Space is vast and mysterious. It holds countless wonders, and among them are stars and the planets that orbit them. We often imagine these celestial objects moving with clockwork precision, their paths predictable and unchanging. But the universe is a place of constant motion, where gravity weaves a complex dance between celestial bodies. Sometimes, this dance is a graceful waltz, like the Earth revolving around the sun. Other times, it's a more intricate ballet with multiple partners moving in a delicate balance. This is the realm of the three-body problem, a puzzle that has intrigued mathematicians and astronomers for centuries. Imagine three stars, locked in a gravitational embrace. Their movements a complex interplay of attraction and repulsion. The three-body problem is a tale as old as physics itself. It begins with Isaac Newton, who in the 17th century laid the foundations of classical mechanics with his law of universal gravitation. Newton showed that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This simple law explained why objects fall to the Earth and why the Moon orbits our planet. But when Newton tried to apply his law to the motion of three bodies, such as the Earth, the Moon, and the Sun, he ran into a problem. The equations became incredibly complex, and he couldn't find a general solution. The problem wasn't that Newton's law was wrong, but rather that the three-body problem is inherently chaotic. Chaos in this context doesn't mean random. It means that even small differences in the initial conditions of the system, such as the positions and velocities of the bodies, can lead to vastly different outcomes over time. The three-body problem, for all its complexity, is more than just a theoretical exercise. It has real-world implications, particularly when we look at star systems beyond our own. Our Sun is a solitary star, but many stars in the Milky Way galaxy exist in binary or multiple star systems. These systems, where two or more stars are gravitationally bound, present unique challenges and opportunities for the formation and evolution of planets. Alpha Centauri, our closest stellar neighbor, is a prime example of a multiple star system. Located just over 4 light-years away, Alpha Centauri is a triple star system, consisting of two Sun-like stars, Alpha Centauri A and Alpha Centauri B, and a smaller, dimmer red dwarf star, Proxima Centauri. The two main stars, Alpha Centauri A and B, orbit each other in a relatively close elliptical orbit, while Proxima Centauri orbits the pair at a much greater distance. The three-body problem, at its heart, is a deceptively simple question. If you know the positions, masses, and velocities of three objects at a given time, can you predict their motion under the influence of gravity for all time? Isaac Newton, the father of classical mechanics, formulated this problem in the 17th century, and it quickly became a thorn in the side of mathematicians and physicists. Newton himself, despite laying the groundwork for understanding gravity with his law of universal gravitation, struggled to find a general solution to this seemingly straightforward problem. The two-body problem, where two celestial bodies interact gravitationally, had a relatively elegant solution. Newton showed that two bodies, like the Earth and the Sun, would orbit their common center of mass in predictable elliptical paths. However, introducing a third body, like the Moon, into the equation throws this elegant simplicity into disarray. The gravitational forces from all three bodies constantly tug on each other, creating a complex interplay of attraction and repulsion that makes it impossible to derive a simple, closed-form solution for their trajectories. For centuries after Newton, mathematicians sought a general solution to the three-body problem. a set of equations that could predict the positions and velocities of the three bodies for all time. However, progress remained elusive. The complexity of the interactions between the three bodies made it a daunting challenge, one that seemed insurmountable despite the best efforts of the brightest minds. It wasn't until the late 19th century that the French mathematician Henri Poincaré made a groundbreaking discovery that would change our understanding of the problem forever. Poincaré's work was not just a step forward, it was a leap that opened new horizons in the field of mathematics and physics. Poincaré, through his work on celestial mechanics, realized that the three-body problem was fundamentally different from the two-body problem. The interactions were not merely more complex, they were of a different nature altogether, involving a level of unpredictability that was previously unrecognized. It wasn't simply a matter of finding a more sophisticated mathematical approach, it was inherently chaotic. This chaos meant that small changes in the system could lead to vastly different outcomes, a concept that was both revolutionary and unsettling. Poincaré's insight was that even tiny differences in the initial conditions of the three bodies, their starting positions, velocities, or masses, could lead to dramatically different outcomes over time. This was a profound realization that had implications far beyond the three-body problem itself. This sensitivity to initial conditions, later dubbed the butterfly effect, meant that long-term predictions for three-body systems were practically impossible. The butterfly effect suggested that the universe was far more complex and interconnected than previously thought. Even the slightest error in measuring the initial conditions would propagate and amplify over time, rendering any long-term predictions meaningless. This was a stark contrast to the deterministic view that had dominated scientific thought for centuries. This discovery was revolutionary because it challenged the prevailing deterministic view of the universe. It suggested that there were limits to what could be predicted, even with the most precise measurements and calculations. Newton's laws of motion were deterministic, meaning that if you knew the initial conditions of a system, you could, in principle, predict its future with perfect accuracy. This was a cornerstone of classical mechanics and had been the foundation of scientific thought for centuries. However, Poincaré's work showed that even within the framework of Newtonian mechanics, there were systems like the three-body problem that were inherently unpredictable. This realization opened the door to the study of chaos theory and had profound implications for our understanding of the natural world. It marked the beginning of a new era in science, one where uncertainty and unpredictability were recognized as fundamental aspects of the universe. The butterfly effect, a poetic metaphor for chaos theory, illustrates the profound interconnectedness of seemingly unrelated events. In the context of the three-body problem, it means that a minuscule change in the initial position or velocity of one of the bodies, a change as small as the flap of a butterfly's wings, can drastically alter the system's long-term evolution. This sensitivity to initial conditions has profound implications for our understanding of planetary systems and the potential for life in the universe. In the vast expanse of the Milky Way, our sun appears as a solitary wanderer, a single star adrift in the cosmic ocean. Yet, we know that stars are often found in pairs or groups, bound together by gravity's invisible hand. For those seeking companions among the stars, one needn't look far. A mere stone's throw away, by cosmic standards, lies Alpha Centauri, our closest stellar neighbor, and a system that has captivated astronomers for centuries. At a distance of just over 4 light-years, Alpha Centauri is so close that its stars are visible to the naked eye in the southern hemisphere. It's a triple-star system, consisting of 2 sun-like stars, Alpha Centauri A and Alpha Centauri B, engaged in a close orbital dance, and a smaller, dimmer red dwarf star, Proxima Centauri, orbiting the pair at a greater distance. Imagine gazing up at the night sky and seeing not one, but 3 suns, their light painting the heavens with a tapestry of colors. Such is the view from a hypothetical planet within the Alpha Centauri system. The Alpha Centauri system, with its 3 stars engaged in a complex gravitational ballet, offers a real-world example of the 3-body problem in action. Unlike the simplified models used by mathematicians and physicists, where point masses move under the influence of gravity alone, real star systems are far more intricate. Factors such as the star's rotation, magnetic fields, and the potential presence of planets can all influence the long-term stability and evolution of the system. One of the key challenges in studying 3-body systems is that their motions are often chaotic, meaning that even small uncertainties in the initial conditions can lead to significant differences in their future trajectories. In the case of Alpha Centauri, the relatively close proximity of Alpha Centauri A and B, combined with the distant orbit of Proxima Centauri, creates a complex interplay of gravitational forces. While the system appears stable on human timescales, its long-term evolution is far from certain. In 2016, astronomers made a groundbreaking discovery within the Alpha Centauri system that sent ripples of excitement throughout the scientific community and beyond. Orbiting the red dwarf star Proxima Centauri, they detected a planet, designated Proxima Centauri b, or Proxima b for short. This exoplanet, a planet outside our solar system, was immediately recognized as special, not just because of its proximity to Earth, but also because of its potential to harbor life. Proxima b is estimated to be at least 1.3 times the mass of Earth, placing it in the category of a super-Earth. It orbits its host star at a distance of roughly 0.05 astronomical units, completing one orbit every 11.2 Earth days. While this close proximity might seem scorching, Proxima Centauri is a much cooler and fainter star than our Sun, meaning that Proxima b resides within its habitable zone. The discovery of Proxima b has ignited the imaginations of scientists and the public alike, fueling dreams of one day reaching this nearby world and searching for signs of life. However, observing and studying exoplanets, especially those around other stars, is a formidable task, pushing the limits of current technology and requiring innovative approaches to tease out information from across the vast gulf of space. One of the primary methods used to detect exoplanets is the transit method. This technique relies on observing the subtle dimming of a star's light as a planet passes in front of it, blocking a tiny fraction of its light. While effective, the transit method requires a fortuitous alignment, as the planet's orbit must be edge-on as seen from Earth for a transit to be detectable. The Alpha Centauri system, with its intricate 3-body dance, presents a fascinating case study in the long-term stability and evolution of star systems. Unlike our solar system, where the sun's gravity dominates the dynamics, the gravitational interactions between the 3 stars in Alpha Centauri create a far more complex and ever-changing environment. Understanding how this system has remained stable over billions of years, and how it might evolve in the future, provides valuable insights into the process that shape planetary systems throughout the cosmos. One of the key factors influencing the stability of multiple star systems is the concept of orbital resonance. Resonance occurs when the orbital periods of 2 or more celestial bodies are related by a simple integer ratio. For example, if one planet orbits its star twice for every one orbit of another planet, the 2 planets are said to be in a 2-to-1 resonance. The Alpha Centauri system, our closest stellar neighbor, beckons us with its promise of other worlds and the tantalizing possibility of finding life beyond Earth. It's a system that embodies both the familiarity of sun-like stars and the alien beauty of a triple-star sky. As we delve deeper into the mysteries of Alpha Centauri, we gain a profound appreciation for the diversity of planetary systems in the universe and the intricate interplay of gravity, physics, and chance that shapes their destinies. The search for life beyond Earth is one of the most profound scientific endeavors of our time. Alpha Centauri, with its potentially habitable planet Proxima b, offers a tantalizing glimpse into the possibilities that await us among the stars. While the challenges of interstellar travel remain daunting, the proximity of Alpha Centauri makes it a prime target for future missions aimed at studying this system in greater detail and searching for signs of life. Science fiction, at its core, is a genre that explores the boundaries of the possible, using the tools of imagination to craft stories that illuminate the human condition against the backdrop of the unknown. In Liu Cixin's acclaimed novel, The Three-Body Problem, the scientific puzzle of the three-body problem takes center stage, serving not just as a plot device but as a powerful metaphor for the challenges of understanding and navigating a complex, often unpredictable universe. Liu Cixin masterfully weaves the complexities of the three-body problem into the fabric of his narrative, using it to create a sense of cosmic dread and wonder. The Trisolaran system, home to an alien civilization on the brink of collapse, becomes a microcosm of the challenges posed by chaotic systems, where even the slightest perturbations can have catastrophic consequences. The unpredictable nature of the Trisolaran sun's movements, swinging erratically between scorching heat and frigid cold, mirrors the instability and uncertainty that permeate the lives of the Trisolarans, and eventually humanity itself. Imagine a world where the rising and setting of the sun is not a predictable, comforting rhythm, but a chaotic lottery, where the very laws of nature seem to conspire against the emergence and flourishing of life. This is the Trisolaran system, as envisioned by Liu Cixin, a stellar environment pushed to the brink of chaos by the gravitational interplay of its three suns. Unlike our solar system, where the sun's gravity reigns supreme, maintaining the planets in stable, predictable orbits, the Trisolaran system is a celestial mosh pit. The three suns, locked in a perpetual gravitational tug-of-war, trace out complex, ever-changing paths, their movements dictated by the intricate mathematics of the three-body problem. The chaotic nature of the Trisolaran system is not merely a backdrop for Liu Cixin's story. It's a driving force that shapes the destiny of civilizations. The Trisolarans, facing the imminent destruction of their world, see in humanity a glimmer of hope, a chance for survival on a distant planet with a stable, life-sustaining sun. Their desperate gamble to reach Earth and claim it as their own sets in motion a chain of events that will forever alter the course of both civilizations. The three-body problem, in this context, becomes a metaphor for the complex interplay between civilizations, each with its own history, motivations, and fears. The unpredictable nature of the Trisolaran sun's movements mirrors the uncertainties and shifting alliances that characterize interspecies relations. Just as the Trisolarans believe they have found a solution to their planetary crisis, new challenges and unforeseen consequences arise, throwing their plans into disarray. In the cosmic chess match between Earth and Trisolaris, the three-body problem becomes a weapon, a tool to be exploited and manipulated in a desperate bid for survival. Both civilizations, facing an existential threat, resort to cunning strategies and technological innovations, their actions echoing the intricate maneuvers of celestial bodies locked in a gravitational dance. Humanity, initially caught off guard by the Trisolaran threat, scrambles to develop countermeasures, their efforts hampered by internal divisions and the sheer scale of the technological gap between the two civilizations. The Trisolarans, meanwhile, exploit their advanced technology and knowledge of the three-body problem to sow chaos and disrupt human progress, infiltrating communication systems and manipulating global events to their advantage. Faced with the impending arrival of the Trisolaran fleet and the realization that the universe is not a benign cradle but a battleground, humanity undergoes a profound transformation. The three-body problem, once a theoretical curiosity confined to the realms of science, becomes an inescapable reality, forcing humanity to confront its own limitations and grapple with the implications of its place in the cosmos. The initial shock and disbelief give way to a wave of global panic and social upheaval. Governments crumble, ideologies clash, and the very fabric of society begins to unravel as humanity grapples with the enormity of the threat. Some seek solace in religion, others embrace nihilism, while others still cling to the hope that science and technology can provide a way out. The Alpha Centauri system, our closest stellar neighbor, offers a captivating real-world example of a three-body system in action. Comprising two sun-like stars, Alpha Centauri A and B, engaged in a close orbital dance, and a smaller, dimmer red dwarf, Proxima Centauri, orbiting the pair at a greater distance. This system presents a complex gravitational puzzle. While the three-body problem in its purest mathematical form often leads to chaotic and unpredictable outcomes, the Alpha Centauri system exhibits a surprising degree of stability, at least on human timescales. The key to understanding the relative stability of Alpha Centauri lies in the specific configuration of its stars. Alpha Centauri A and B, the two main components, orbit each other in a relatively close elliptical orbit, with a period of roughly 80 years. This close-knit dance creates a strong gravitational bond between them, effectively treating them as a single, more massive object from the perspective of the more distant Proxima Centauri. In stark contrast to the relative stability of the real Alpha Centauri system, Liu Cixin's The Three-Body Problem plunges us into the chaotic and unforgiving depths of the fictional Trisolaran system. Here, three suns engage in a celestial mosh pit, their movements dictated by the unpredictable whims of the three-body problem, creating a nightmarish environment for any planet caught in their gravitational web. The Trisolaran system, unlike the hierarchical structure of Alpha Centauri, lacks a dominant gravitational center. The three suns, each with its own mass and orbital characteristics, engage in a constant tug-of-war, their gravitational influences constantly shifting and pulling at each other, creating a system perpetually on the brink of collapse. The three-body problem, despite its deceptive simplicity, has captivated mathematicians and astronomers for centuries, driving the development of new mathematical tools and pushing the limits of our computational abilities. From Isaac Newton's early attempts to find a general solution to the problem to the advent of modern supercomputers capable of simulating the intricate dances of celestial bodies, the quest to understand the three-body problem has profoundly shaped our understanding of the universe. Newton, despite laying the groundwork for classical mechanics with his law of universal gravitation, recognized the inherent complexity of the three-body problem. He was able to solve the simpler two-body problem, where two objects orbit their common center of mass in predictable elliptical paths. However, the addition of a third body introduced a level of complexity that defied his mathematical prowess. The three-body problem, both in its mathematical formulation and its real-world manifestations, teaches us a profound lesson about the limits of prediction and the importance of embracing uncertainty. While Newton's laws of motion provide a deterministic framework for understanding the universe, chaotic systems like those governed by the three-body problem demonstrate that even within this framework, predictability is not always achievable. In chaotic systems, tiny differences in initial conditions, such as the positions and velocities of the bodies involved, can lead to vastly different outcomes over time. This sensitivity to initial conditions, often referred to as the butterfly effect, means that even with perfect knowledge of the laws of physics, our ability to predict the long-term behavior of such systems is inherently limited. Science fiction at its best not only entertains but also inspires, pushing the boundaries of imagination while grounding its speculations in the realm of scientific possibility. Liu Cixin's The Three-Body Problem exemplifies this synergy, using the scientific puzzle of the three-body problem as a springboard for exploring themes of cosmic dread, the fragility of civilization, and the challenges of interspecies communication. While the chaotic and extreme nature of the trisolaran system in Liu Cixin's novel serves as a dramatic plot device, it also highlights the very real challenges that astronomers face in understanding and predicting the behavior of multiple star systems. The novel sparks our curiosity about the diversity of planetary systems in the universe and the potential for both stability and chaos in their evolution. In the vast expanse of the cosmos, where stars ignite and fade like celestial fireflies, the search for life beyond Earth hinges on a delicate balance of cosmic conditions. Central to this search is the concept of the habitable zone, a region around a star where temperatures are just right, not too hot, not too cold, for liquid water to exist on the surface of a planet. This Goldilocks zone, as it's often called, represents a sweet spot for life as we know it, a cosmic oasis where the chemistry of life can flourish. The habitable zone is not a fixed boundary, but rather a fluid region, its size and location determined by the star's luminosity and temperature. Hotter, more massive stars have larger, more distant habitable zones, while cooler, less massive stars have smaller, closer-in habitable zones. In the chaotic realm of the trisolaran system, as imagined by Liu Cixin, the concept of a stable, life-friendly habitable zone takes on a nightmarish twist. With three suns engaged in a perpetual gravitational tug-of-war, the very notion of a predictable, temperate region around any of these stars becomes a distant dream. The erratic orbits of the trisolaran suns create a celestial game of cosmic billiards, where the habitable zone is not a fixed ring, but a constantly shifting and shrinking target. At times, two or even all three suns might align, their combined radiation bathing the trisolaran planet in scorching heat, boiling away any oceans and sterilizing the surface. The Alpha Centauri system, our closest stellar neighbor, presents a more nuanced and optimistic picture for habitability, albeit with its own set of challenges and possibilities. With two sun-like stars, Alpha Centauri A and B, and a smaller, dimmer red dwarf, Proxima Centauri, this triple-star system offers a tale of two habitable zones, each with its own unique characteristics and potential for harboring life. Alpha Centauri A and B, with their close binary orbit, present a combined habitable zone that's slightly wider and shifted slightly farther out compared to our Sun's habitable zone. Planets orbiting within this zone would experience a double dose of sunlight, their skies graced by two suns, but their overall radiation exposure would be within the range considered suitable for life. In the cosmic dance between planets and their stars, gravity plays a powerful role, not only dictating orbital paths, but also influencing the very rotation of worlds. For planets in close orbits around their stars, especially those orbiting red dwarf stars, tidal forces can create a phenomenon known as tidal locking, where the planet's rotation period becomes synchronized with its orbital period. In essence, the same side of the planet always faces the star, much like how the moon always shows the same face to Earth. Stars are not the static, unchanging beacons of light we often imagine them to be. They are dynamic and often tempestuous objects, capable of unleashing powerful bursts of energy that can have dramatic consequences for any planets orbiting within their reach. Red dwarf stars, despite their diminutive size and low luminosity, are particularly notorious for their frequent and intense flares, sudden releases of energy that can bathe nearby planets in harmful radiation. These flares, often compared to supersized solar flares, are thought to be driven by magnetic activity in the star's outer layers. When magnetic field lines reconnect and realign, they can release vast amounts of energy in the form of radiation, including X-rays and ultraviolet radiation, which can strip away a planet's atmosphere, or even boil off liquid water on its surface. In the grand tapestry of the cosmos, woven with threads of gas, dust, and starlight, the search for life beyond Earth stands as one of the most profound and challenging endeavors ever undertaken by humanity. While finding a planet within the habitable zone of a star is a crucial first step, it's merely the opening act in a cosmic drama that seeks to answer one of humanity's oldest and most fundamental questions. Are we alone? To determine whether a distant planet harbors life, astronomers are developing increasingly sophisticated techniques to detect signs of life, or biosignatures, in the planet's atmospheres or on their surfaces. These biosignatures, like subtle whispers carried across the vast gulf of space, hold the potential to reveal the presence of life, even if it's vastly different from life as we know it on Earth. Our quest to unravel the mysteries of the cosmos, to peer into the depths of the universe and uncover the secrets held within distant star systems like Alpha Centauri, hinges on our ability to see beyond the confines of our planet. Just as Galileo's first telescope revolutionized our understanding of the heavens, revealing the moons of Jupiter and the craters of the moon, so too do modern telescopes, equipped with cutting-edge technology, push the boundaries of human perception, allowing us to probe the cosmos with unprecedented clarity and precision. No longer limited by the constraints of Earth's atmosphere, which blurs and distorts incoming starlight, space-based telescopes like the Hubble Space Telescope and the James Webb Space Telescope orbit high above Earth, capturing breathtaking images of distant galaxies, nebulas, and star-forming regions. For centuries, astronomers have yearned to observe the cosmos with the same clarity and sharpness as if they were peering through the vacuum of space. Earth's atmosphere, while essential for life, acts as a giant lens, bending and scattering incoming starlight, creating the twinkling effect we observe with the naked eye. While charming to behold, this atmospheric turbulence severely limits the resolution of ground-based telescopes, blurring the fine details of distant celestial objects. Light, the cosmic messenger that carries information across vast stretches of space and time, holds within its shimmering embrace a wealth of secrets about the universe. Spectroscopy, the study of how light interacts with matter, provides astronomers with a powerful tool to decode these secrets, revealing the chemical composition, temperature, motion, and even the history of celestial objects. When light from a star, galaxy or nebula passes through a prism or a diffraction grating, it's spread out into its constituent wavelengths, creating a spectrum, much like a rainbow. This spectrum is not merely a beautiful display of colors, but a cosmic fingerprint, containing a wealth of information about the source of the light. The era of big data has arrived in astronomy, bringing with it both unprecedented opportunities and daunting challenges. Telescopes are now generating terabytes of data every night, capturing images of billions of stars and galaxies, mapping the distribution of dark matter, and searching for faint signals from the early universe. Analyzing this deluge of data, extracting meaningful insights from the cosmic noise, has become a Herculean task, pushing the limits of traditional data analysis techniques. Enter artificial intelligence, or AI, a powerful new tool that's rapidly transforming astronomy and our ability to understand the universe. Machine learning, a subset of AI, allows computers to learn from data without being explicitly programmed, identifying patterns, making predictions, and even discovering new phenomena that might have eluded human observers. As we gaze up at the night sky, our eyes drawn to the twinkling tapestry of stars, we are reminded of the profound mysteries that lie beyond the confines of our planet. The vastness of the cosmos, its sheer scale and unimaginable beauty, both humbles and inspires us, igniting a thirst for knowledge that has driven humanity's exploration of the heavens for millennia. From the ancient astronomers who charted the movements of the planets with meticulous care, to the modern astrophysicists who probe the secrets of black holes and the origins of the universe, our fascination with the cosmos has been a constant thread throughout human history. The stars have served as celestial guides for navigators, as timekeepers for farmers, and as sources of wonder and inspiration for artists, poets, and dreamers. Alpha Centauri, with its proximity to Earth and its intriguing system of stars and planets, holds a special place in our imaginations as a potential stepping stone to the stars. While the challenges of interstellar travel remain daunting, the dream of one day sending a spacecraft to this nearby star system, of capturing close-up images of its planets, and searching for signs of life, continues to inspire scientists, engineers, and space enthusiasts alike. Several ambitious projects are underway to develop the technologies needed for interstellar travel, from laser-powered sails that could propel tiny spacecraft to relativistic speeds, to fusion-powered engines capable of generating the immense thrust required for a crewed mission to another star system. While these technologies are still in their early stages of development, the sheer audacity of the goal of reaching for the stars is a testament to the boundless potential of human ingenuity. Beyond its scientific significance, the three-body problem has captured the imaginations of writers, artists, and filmmakers, serving as a powerful metaphor for the complexities of human relationships, the challenges of navigating uncertainty, and the search for meaning in a seemingly chaotic universe. Just as the three bodies in a gravitational dance are locked in a constant struggle for balance, so too are human beings often pulled in multiple directions by competing desires, loyalties, and beliefs. The unpredictable nature of the three-body problem mirrors the uncertainties and complexities of human relationships, where even small changes in behavior or circumstance can have dramatic and unforeseen consequences. Science and fiction, often perceived as separate domains, have the power to enrich and illuminate each other, revealing new perspectives on the human condition and inspiring us to explore the unknown with both curiosity and a sense of wonder. The exploration of Alpha Centauri and the three-body problem exemplifies this fusion of fact and fiction, showcasing how scientific discoveries can spark the imagination and how fictional narratives can deepen our understanding of complex scientific concepts. As we delve deeper into the mysteries of the cosmos, guided by the scientific method and fueled by the power of storytelling, we gain a richer and more nuanced understanding of our place in the universe. Science provides us with the tools to explore the physical world, to unravel the laws of nature, and uncover the secrets of the cosmos. Fiction, on the other hand, allows us to explore the human heart, to grapple with ethical dilemmas, and to imagine the possibilities and consequences of our actions.